Welcome again, everyone, to our episode number 70. It has been quite a journey. We are very happy and delighted to have Tapomayukh Bhattacharjee today from Cornell. Just to give a brief introduction, so Tapo is an assistant professor in the Department of Computer Science at Cornell, where he directs the Emprise Lab. I think someone can put the link here. He completed his PhD in robotics from Georgia Tech and was a NIH Ruth L. Kirstein NRSA postdoctoral research associate in computer science and engineering at the University of Washington, UW. He wants to enable robots to assist people with mobility limitations with activities of daily living. His work spans the fields of human-robot interaction, haptic perception, and robot manipulation, and focuses on addressing the fundamental research question on how to leverage robot world physical interactions in unstructured human environments to perform relevant activities of daily living. He is the recipient of NSF Career Award 23, and his work has won Best RoboCup Paper Award at IROS 22, Best Paper Award finalist, Best Student Paper Award finalist at IROS 22, Best Technical Advances Paper Award at HRI 19, and Best Demonstration Award at NeurIPS 18. His work also been featured in many media outlets, including the BBC, Reuters, New York Times, IEEE Spectrum, and GeekWire. And his robot-assisted feeding work was selected to be one of the best interactive designs of 2019 by Fast Company. We are very happy to have you, Tapo, and I will stop sharing my screen here. You can take it away.
Thanks a lot, Riddhi. Very kind introduction, and happy to meet you all. So, hi everybody. As Riddhi mentioned, this is me, but you can just call me Tapo because I think it can be a difficult name to pronounce, my full name. And here is my lab's website. And today I'm going to focus on, my work on, robotic caregiving or towards robotic caregiving. And we are a lab, a full stack robotics lab that builds robots, that work alongside human stakeholders. Before I start, here is my entire lab. Well, at least at that time, the work that I'm going to present would not be possible without they are the ones who are actually doing the work. So I'm just presenting this. Okay. So in general, my lab's goal is to enable robots to assist people with mobility limitations with different activities of daily living. Now, when I say activities of daily living, there is a wide variety, and like if you just look at the US, there are even an old survey says that there are 24 million adults that need assistance with tasks of daily living. And worldwide, it's much higher, right? And these activities of daily living are basically, there are some basic activities such as feeding, dressing, transferring that people generally do daily, right? And there are some instrumental activities like housework, laundry, meal preparation. And these ADLs, as you can see, they have a wide variety of physical and social interactions here, right? Where the human caregiver is physically interacting with the care recipient in this case, and on not only the care receiver, but also the objects around the care receiver. Now, human caregivers, they're doing an amazing job. I mean, hats off to them. But even after that, right, care recipients may sometimes feel embarrassed, rushed, or socially challenged because there is a lack of control and independence in these tasks. And these are not some words that I made up. When I visited these assisted care facilities, they basically told me exactly these words to express how they felt, right? Like imagine yourself asking somebody else to feed you every morsel of bite in your day-to-day life. It really takes away the feeling of independence. Now, some of the activities are not only it's not just for the care recipients, but even for caregivers. They can become especially time consuming. Like for example, this feeding activity. And it increases caregiver burden, which decreases the quality of care for some of the other activities where their expertise could be used. So the question that my lab asks is like, can robots be used for these kinds of activities? Now, robots have the potential to help, right? Like, for example, here you see Kinova, which is one of the largest assistive arm manufacturer in North America. They are like, you see these Kinova arms mounted on wheelchairs and being used by actual people, like people with disabilities, various kinds of disabilities in their home, to do various things, like whether it's picking up a remote, opening a fridge, opening a drawer, or even interacting with, with their grandkids and things like that, right? However, like most of these things that you see, a person has to, teleoperate the robot. What I mean by that is the person has to command the robot to do certain things, and the autonomy that is there in the robot is actually limited. And so what we are trying to see is that, can we add some more intelligent autonomy to this, so that, these robots can truly become, companions for these people in their homes and do various tasks. However, building, these caregiving robots is very challenging. And I'm going to give you some idea of why this is challenging, right? It's because caregiving in general is very multifaceted and contextual. So for example, like, let's look at these two videos, right? Like here you have two people, Tyler on the left, and on the right, it's Henry. They are both being assisted with the same activity of feeding, right? But if you see, like Tyler's mother brings the food near Tyler's mouth, and then Tyler is to, move his neck to actually do it because he has some neck mobility. But on the right, Henry actually cannot do that. And he can only chew from one end of the mouth, one side of the mouth. So Henry's caregiver, William here, in this case, places the food directly under that part of the mouth where Henry can actually bite. So even the same activity, depending on a care receiver's functional abilities, can result in very different control policies or manipulation policies. Let's look at, like, this is about functional ability, right? They can also have very different behavioral traits. Tyler used to, watch video, like basically watching, eat while watching baseball. Baseball used to be his favorite pastime. By the way, I don't know if you noticed this. I'm always saying Tyler used to, because, a few months back, Tyler actually passed away. But yeah, he was an amazing collaborator for us. So on the right, you have Henry Evans, and he basically shows his intent to take a bite by looking at the person and opening the mouth, and then caregiver knows to feed them. So again, the same activity, but very different control policies, because they have different people may have different, like behavioral traits, right? So, and it's not just that, they may also reside in different environments. Here, it's Henry, the same care receiver, the same caregiver, William, but they are being transferred either when a Sarah lift is present, using a very different control policy than when William is directly lifting him and taking him from bed to wheelchair. And here, another thing, it also, the manipulation policies also depend on the caregivers. Like here you see on the left, you see William, who is actually helping. Actually, let me see if the video runs. I am on the right. Yeah. So on the left, you see William helping dress a pant on Henry, which is very different from his wife, Jane, who is doing the same activity, but in a very different way. So the point that I want to make is that caregiving is very multifaceted. It is contextual on the user's functional and behavioral traits. It is dependent on the surrounding environment where the care receiver stays. It is also dependent on the caregiver as well as the robot that you will use, because the robot will have different workspace constraints, different payloads and things like that. And even if you are helping with the same activity, you may need very different control policies to adapt to all of these things. This is why building caregiving robots is very hard. And even if you don't remember anything from my talk, I would want you to pay attention to this slide, which basically says that the key insight that I have learned from my experience working in this area is that to really make meaningful progress in this field, we need to involve stakeholders from the initial design phase to the experiment and evaluation phase as well. And what I mean by stakeholders are not only the care receivers themselves who you are trying to help, but also caregivers and occupational therapists and everybody else with whom this technology can impact. Now, before trying this out in the real world, I also think strongly that we need to be able to simulate and prototype so that we can figure out various safety and other related issues, and then move on to the real world deployment. But of course, simulation is never a substitute for real world deployment. It's just a way for us to go there. So with that, I'm now going to jump into the technical aspects of different projects that I'm going to show. And I'm going to, again, because of the time limitation, I'm not going to be able to dive deep into these. And that's where you can ask me questions later on after my talk. But I'm going to give you a high-level overview of different projects that are going on with this aim, right? So first, as I mentioned, we need simulators for prototyping these solutions, these caregiving solutions. When we started working on this field, we found actually there was a significant lack of realistic simulators where you model the mobility limitations of human stakeholders. And that's what we want to focus on. There's a lot of simulators for robot manipulation in general, for robot rigid body manipulation. And sometimes even there is a lot of progress these days on soft body manipulation. But with human-robot interaction and physical human-robot interaction and assistive robotics, there is actually a huge gap. So this is where we started this project called Arcare World. It's a simulator that our lab has developed. Now, what is Arcare World? Here is a video. Here you see there's a person with cerebral palsy who has involuntary motions. By the way, all of these motions and the dimensions of the person that you see are from actual clinical data that we collected in the real world, right? And you see this Toyota robot helping this person with this activity of feeding. So how did we build this Arcare World? Before we started building this simulation environment, we wanted to see what are the components that are necessary for this. So we found that, of course, we need realistic human avatars that have realistic range of motion and muscle strength, because we are simulating disabilities here, like physical disabilities. As well as we need to be able to model behavioral routines, as I mentioned before. We also need caregiving home environments, not like normal home environments, like usual home environments people have, but also home environments with modifications that may help with these activities, and also presence of assistive devices such as wheelchairs and things like that. And in addition, of course, we need other things that typically are there in other robotic simulators, such as support for different robots, multimodal sensing, as well as multiple interfaces, right? So when I say multiple interfaces, basically interface for ROS, Python, as well as virtual reality, as well as support for planning, learning, and control. Both robot as well as humans, because humans are agents, active agents in this simulator. So to be able to do that, let me first focus on the care avatars, right? So the way we built care avatars was each of the caregivers, care avatars have skin built on top of muscles, built on top of bones. And we manually model each of these using Hill muscle model. And we calibrated this by collecting actual clinical data, which occupational therapists actually helped us to collect clinical data from the real world. And then, so here is, for example, a musculoskeletal actuation system that we have for each of these avatars. In addition, we also have soft tissues on top of a skeletal model. So here on the right, you will see you can model deformation as well as a lot of stress. Let's say if I'm accelerating a wheelchair in a synthetic scenario, you can see stresses that happen in different muscles that are shown. Red means high stress, yellow means lower stress, right? And then you also have soft tissues, like for example, even in tongue, like how can we simulate interactions, food-tongue interactions and things like that. So in the version 1 of Arcare World that we have released, we have 6 care avatars that we have released, people with different kinds of spinal cord injury, cerebral palsy, left side hemiplegia, as well as brainstem stroke. Of course, the Arcare World simulator is a generic simulator. You can build your own avatars. The only constraint is you need clinical data. Clinical data to have their dimensions, their muscle strength, and the range of motion, active range of motion, as well as passive range of motion, so that you can model these physical disabilities in a realistic way. In our version 2, we'll add more avatars, but if you have the data, you can build your own avatars right now. In addition to these care avatars, we have care homes. By care homes, basically, I mean, homes that have physical, home modifications. So we have level 1 homes that are like, normal homes. Then we have partially barrier-free homes, level 2, and then level 3, which are completely barrier-free homes. How did it build this? Again, by using universal design manual for, barrier-free homes modifications. And robots can learn different skills for different kinds of, home modifications. So for example, like different knobs for opening door that different people with limitations may prefer. We have released our version 1 has been released with different kinds of kitchens, bedrooms, 60 bedrooms, 70 bathrooms, living rooms, and each with different level 1, level 2, and level 3 modifications. In addition to this, we have assistive devices like actuatable hospital bed, toilet Sarah lifts, Hoyer slings, wheelchairs, and various other things. In addition, we have support for different kinds of caregiving robots. And again, you can add your own robots using URDF. We have support for, of course, visual sensing, both RGB as well as depth sensing, and force torque sensing, like not only at the end effector, as you see in this video, but also whole arm sensing that is very useful for various caregiving tasks where the robot needs to come in contact, not only at the end effector, but all across the arm. We have support for, we have different interfaces where it's based on Unity, but on the other end, you have support for Python, ROS, as well as virtual reality for collecting demonstrations. And in addition to connecting with learning libraries such as Stable Baselines 3 and OpenAI Gym, you can also connect it with planning libraries such as MoveIt and OMPL, as well as different VR devices. So you can, and these are not only for just the robots, but also for the humans. And when we release this, we also release benchmark different robotic caregiving tasks with different our reinforcement learning policies. But feel free to use whatever policies you want. Here is the current community. Actually, this is different. It's a little bit old slide. We have more people now, and we have released this around maybe 2 months back, and it has already gotten some traction, and we are getting feedback from people, and we are continuously, improving the simulator. So yeah, RKL basically has the capability to be able to, at least it's a good first step to be able to do these kinds of robotic caregiving tasks and simulate them. But my lab is all about real world deployment, right? Simulation is just a way to go towards real world deployment. And we have done lots of different works in real world deployment in different areas, but we'll see how the time is. But for now, first, I'm going to just focus on a feeding work that we have done that is probably the most mature in our lab. So feeding, right? Now, the first thing about feeding is that, of course, feeding is an activity of daily living. And so it's an important task to solve, but it's also a very challenging task because it's a very intricate manipulation task, right? And we asked actually one of JECO. JECO is the Kinova's, the older version of the the Gen 2, basically, it's called. Now the new name. The old name was JECO. And so this JECO robot user, expert user with C1 quadriplegia, we asked them, right? How long would it take for them to, pick up, different kinds of food items, even solid food items? I'm not even talking about the video, with this video where it shows much more subtle manipulation strategies. And they said it would take them around 45 minutes. So that means just relying on teleoperation is not going to work here. We need intelligent autonomy. And it is challenging because you need deformable object manipulation during bite acquisition, but you also need physical human, like robot interaction during bite transfer, right? Like to be able to come and feed somebody inside the mouth. And so I'll show you first our result, which is our autonomous robot-assisted feeding system. And then I'll dive deep into how we actually did this. And again, it's going to be on a high level. First, so this is our robot-assisted feeding system. Here, the robot goes, picks up a tool of its choice. Like here, it's a fork. It could be spoon. It could be chopsticks. Then it identifies, there are plates. It identifies different food items. The algorithms on the back end tell you what kind of strategy to use to pick up a food item. It uses both vision and haptics to be able to figure out the policy. And then it feeds somebody and orients the food item in such a way so that it's easier for the person to take a bite. Now, of course, in this video, I want to clarify something very carefully because I work in this area. This person that you see the video with, this person does not have a disability, physical disability or visible disability. And so, like, this person is an actor, it was an undergraduate student, but later on I will show videos of our robots actually feeding people of a wide variety of physical disabilities. All right, so generally we divide this work of feeding into two parts. Okay, first is how do you pick up food items, which is bite acquisition, and then the second is how do you transfer the food, which is bite transfer. So the first, let me talk about how we approach this problem of bite acquisition of food items that are deformable. And one thing to, again, like to clarify, right? Like the food item, it's very challenging because some food items are hard, some are slippery, some are soft, some have hard skin but soft inside, like a grape. And it's very difficult. You cannot just use a simple strategy to pick them up. We actually tried that, but it failed when you want to increase the variety of different food items, right? And so we first thought, like, how do we even go about programming a robot to do this? And to do that, we first realized, oh, we as humans, we are experts, right? We are eating food during breakfast, during lunch, during dinner, all the time. So why don't we like see what humans do? So we actually collected a data set of humans, and probably this was a thing that people like this person, like they probably had the most expensive fork that they would ever pick up food with. It had 4 stock sensors, motion capture markers, and instrumented basically to collect different kinds of data. Just to show you the complexity, right? Like this person was trying to pick up a slippery piece of banana, it fell down, and then they failed basically, and then they changed something so that it was able to pick it up. While it may seem very ingrained like in us, what basically they were doing was they were tilting the fork to be able to pick it up. And the reason tilting works is because when you tilt the fork, banana, the weight of the banana, the gravity vector has a component that creates friction, and that stops the banana from slipping across the fork. Like there are so many other strategies that we found that people are using to be able to pick up these things that people like we use daily in our day-to-day life, and we don't even realize this, right? So based on that, we developed a taxonomy of different bite acquisition strategies. And we found that it's not only these, they are visible, like not only they are visible visually, like in terms of visually they are different, haptically also people are using very different forces because, and it's so different that let's say if you use your favorite algorithm, in our case, it was temporal convolution networks, even with just 0.5 seconds of contact after hitting the food item, 0.5, not even a second, it has enough content to be able to tell the difference between different categories of food items such as soft, medium, hard skin, or hard. So we realized that the control policies need to be multimodal. They need to be visual as well as haptic. So the first step is to build the hardware. So for real world deployability, we actually built the hardware. There are a lot of changes we did. I saw Kinova Nathaniel in our audience today. We actually drilled. So this JCO arm did not come with this in-hand camera, right? So we actually drilled a hole in the Kinova arm. We got the power from inside. We made this wireless perception module. And then this wireless perception module supports both these RGBD sensor, the RealSense one, as well as we developed a tactile sensor that can sense shear forces, which is more relevant for our work on the fingertips. And the reason for us to do this is, like, if you place the wire, if you place this this particular camera somewhere far, there are wires coming off. Now in a lab video, that will work great. Imagine feeding somebody in the real world with wires dangling. Wires will get entangled. We have seen this. So even for a trivial problem like this becomes very important to develop systems that are ready for real world deployment. So we had to spend a lot of time to prepare hardware with less number of wires, exposed wires, and that can continuously feed people all over, all the time, right? So once we build this hardware and it can collect multimodal signals, both vision as well as haptic, here is our initial track, right? Where we looked at supervised learning. And the idea was this, right? Given an image of a plate, first we use RetinaNet fine-tuned. It's an off-the-shelf network that we fine-tuned on food images using both simulation data as well as real data. And that creates bounding boxes of food items. Now, each of this, now a person who's sitting on the wheelchair says, hey, robot, feed me a strawberry. Hey, robot, feed me watermelon, feed me mashed potatoes. So based on that, we know which particular food item the bounding box goes inside. Now that goes into a different network that we call SPANET. This is a network that we developed in our lab. It's called Skewering Position Action Network. And that goes inside this, right? And that outputs an action score map that for those food items, what is the best action to take and what is the probability of success? And our action space are actions from that taxonomy that we developed by studying humans, right? But now one thing we realized is that just getting the food item itself is not enough. So for example, to give you intuition, how you would pick up a strawberry or a carrot, piece of a carrot, when it's just at the center of the food item, like of a plate, versus near the wall of a plate, versus if it's stacked on top of a salad, is very different. You use different strategies. So surrounding environment also matters. So that's why we also have a separate module that classifies the environment, and we pass this as a one-hot encoding vector before the final layer so that it does not get dominated by this high-dimensional image before. And where the network uses both of this information to come up with this action score map. So using this, we actually were able to see that robot was able to not only pick up food items, also it was able to generalize. And I put this in quotes because it's a very loaded term, right? Like it was able to generalize to some unseen food items for which the shape or size was similar or the visual characteristics were similar. So for example, if it knows, if in the training data, it knew how to pick up a lettuce, it will know how to pick up, let's say, a spinach or something like that, right? And so there was limited generalization. But what we realized after when we are, again, before going to deployment is that food is diverse. Like in a typical grocery store, there are like 40,000 food items. In my home, I'll suddenly cook up a new dish. So there's no way a supervised learning can have all these things in its training data. And there is going to be distribution shift when we actually try this in the real world. So that's where we started looking at, can we leverage online learning for this? And basic idea of online learning, again, is like, observe a state. You have an action space from which you sample something. You observe a reward and you update your policy, right? And so we modeled this byte acquisition as a contextual bandit problem, where basically the idea is that you observe a context. It could be an image, like some kind of feature from the food item. Then you take an action. The action is, again, the action space is from that same taxonomy that we developed. And then your reward could be just binary. Like we are looking at just byte acquisition now, right? So whether it's success or failure, like whether the food item was on the fork or not after this policy was taken. So again, here is a high-level overview of this. And again, I'm happy to go deeper into each of these later on. But basically, the top part is similar, right? Like you saw our algorithm where we use SPANET. But now, instead of directly saying what object is useful, like what action is useful for picking up a food item, the SPANET gives out a feature. And that feature, we use that, basically that featureizer using that context. That is our context. Using that, we sample an action, okay? We select an action. We don't know what is the right action because we have never seen the food item. And then we actually perform that action. And we see, was that action successful or not? We observe binary reward, and that, based on that reward, it updates the policy. To be able to do exploration, we used LinUCB, the algorithm LinUCB, to trade off between exploration and exploitation. I can go deep into this a little bit more later. But it works better than epsilon greedy because it has because it looks at upper confidence bound, and so it sacrifices some learning speed but improve regret. It gives you improved regret. So using this, here is a live video of how the robot learns how to pick up a banana. Right? You will see a video where the robot doesn't know how to pick up the banana. The right action is the TA action, the red one. You see the confidence is low. Now it's trying continuously. and it's getting reward. And over time, it's going to learn how to pick up this banana. And then it's going to, like, its confidence will increase on that right action, which is the TA action, the tilted angle action. But once it learns, it is always successful. And it doesn't forget other actions that it has learned over time. But obviously, there was a catch here, right? It took us a lot of trials to converge to this. Again, in a real world, like, this banana is going to be destroyed if we keep trying on one piece of banana, right? So we actually further improved this algorithm by not only look at visual context, but also haptic context. And basically, the idea here is that an object, a food item, to the mapping from food item to success is the same. Whether we look at the context, which is the visual, or the post hoc context, which we mean the haptic context, because it happens after an action is taken, the mapping is the same. So we look at both of these things, and the mapping to loss is the same, right? And we optimize both of these models simultaneously, because now we have an extra information. So basically, we look at we do regression on context, but also we do regression on post hoc context. And we force that the mapping from the visual context to the haptic post hoc context, P, is the same, because it's coming from the same object. So it should be the same whether it's successful or not. So what, in terms of the algorithm, basically everything is same, but in addition, we have now a separate featurizer called a haptic net. So this featurizer also goes in addition to the SPA net, and we optimize both of these models simultaneously. We jointly optimize this to be able to converge to an action. And we found that this actually converges to the right action much faster. Okay. So with that, we thought, okay, we are at a mature enough state to try out bite acquisition in the real world. But that's only half the story, right? Once we pick up the food, we need to transfer it to somebody's mouth. So how do you transfer it to somebody's mouth? And here we need to be very careful, because, you know, some care recipients who have very severe mobility limitations, they would require inside mouth transfer. Like, you have to actually bring the food inside the mouth, because they cannot even move their neck. And for them, they also have some other derivative medical conditions that happen. So for example, let's look at this, right? This video. Now here is a person with multiple sclerosis. Do you see what's happening? Like, after every 1 second or 1.5 seconds, you see the person's entire body moving. That's spasm. This person is having spasms. And you, like, there is no, even though you feel like in this short video it's periodic, it's actually not. It's very difficult to predict those. Some other people, as I mentioned, when I showed you video of Henry, they can only chew from one end of their mouth. And sometimes they do in-mouth manipulation, where they use the tongue to guide the robot. Like, imagine a robot that is so heavy, right? It's a metallic robot. You use just your tongue to manipulate, like, and move them inside the mouth, so that it goes somewhere where the person can actually chew, right? It needs to be really, really compliant and safe, right? So the question is, how do you safely and effectively feed these care recipients who have such severe mobility limitations with both voluntary, such as this in-mouth manipulation, or involuntary movements, such as spasms? To do that, basically, we realized that we need really real-time head state estimation, as well as physical interaction classification. And the robot needs to be really reactive to adapt to this physical interaction classification. So here is an example of this person. Here, this person is eating yogurt, and it's a voluntary movement, right? And this person is happy with it.
Perfect.
Now, on the right side,
really
you will see a video. While the robot is trying to feed the cantaloupe,
really
the person suddenly, wait for it. Let's see if the person comes closer. See this movement? That was a spasm. And the robot interact.
With my spasm. Perfect. But it did well with
Like, the robot has to real-time interact with this. And this is happening before. It can even happen when it's inside the mouth.
And it retracted.
So to be able to feed these people,
Me, so that's good.
we had two different modules. One is a multi-view head perception module, which we call FEMTO, where the idea is we had two cameras on the Kinova robot, top and bottom, so that occlusions, and we can cover as much occlusions as possible. And using that, we had encoders that gives output of these different parameters, flame parameters that are basis for like, that we use for reconstructed head model. And then from there, we get dense 2D phase key points. And from the depth data of the camera, we get we get 3D points that we register based on the correspondence. So, and this runs almost like, at if I remember correctly, 15, 20 hertz or so, like real fast. So we had to do we had to be really careful about, the code that we write and everything, so that's really fast. But in addition to this, that's like head perception, we need physical interaction classification, right? So for example, here, like for example, there could be collisions because some people may not be able to open their mouth widely. So the robot needs to be compliant, and the robot needs to remember that if that happens, that, hey, the goal remains the same, it's just that you need to readjust how you move. These are called incidental contacts. There can also be impulsive contacts, like spasms that I showed you. And there, the robot needs to immediately switch. The moment it detects that it's an impulsive contact, it needs to immediately switch to a force tracking controller because it shouldn't hurt the person. There can be in-mouth manipulation, as I mentioned. And here, that not only you need to switch force tracking controller, you need to remember. You need to learn, because it's like learning from demonstrations. It's only that the person is giving demonstration using their tongue. So the robot needs to remember where the person moved the robot using their tongue, so that next time the robot feeds them there, right? So it needs to learn the goalpost. And finally, robot also needs to realize when is the bite taken, because then it needs to move out. So we developed also a physical interaction classification module that can classify all of these different contexts. And then you can decide which controller to use, whether it's a goal tracking controller or a force tracking controller. And all of these are definitely very compliant controllers, right? So here is the entire system diagram. We use multimodal sensing, both visual and haptic sensor. We have a head perception module as well as a physical interaction classification module. Now note, these are all for hardware, these are all for software compliance. What if software fails? What if sensor fails? We also need compliance in the hardware, because we are testing this with real people. I'll show you videos, right, in their homes. So what if the software somehow fails, or, right? Like if you have worked in robotics, robots fail all the time. What if sensors sometimes fail? So even in the hardware, we added compliance where, let's say if there is, like with a certain amount of force, the tool itself will break off and it doesn't fall on the person, it just folds back. And it's safe, the interaction is safe. And we tested it, a lot, right? So here is, so basically once we thought, okay, we were at a mature state that now we have both the acquisition and the transfer. So now are we ready to actually deploy this? So before deploying, we wanted to also test how do we, where are we compared to, some of the other commercial assistive devices for feeding that exist. One of the things, more popular ones in North America is OB. So we actually compared both of these, and we compared this based on different kind of things that we think are important, like metrics that are important to evaluate feeding devices or assistive devices in general. Technical function, can it actually do the function? Robustness, can it adapt to different environments? Information gaps, can the user communicate with it? Can the robot communicate with the user? Usability, can he adapt to users' preferences? User empowerment, social acceptance, will people actually use this? System integration, how well it can integrate with other devices that are there in wheelchairs and around in a person's home. And we found that, yes, our system had higher technology robustness and everything because of intelligent autonomy. But at that time, we still hadn't tested this with real people. And OB, even though it is not very widely used, it is still used by some people, right? Or at least they used it and even before stopping to use it. So then we actually evaluated this with intended care recipients. First, we tried with spinal cord injuries, people from C1 to C6. C1 being the most, severe limitation, and C6 a less severe limitation. We tried out different things, different speeds, interfaces, modes of autonomy. And what we found, something very interesting, was that, we did a study, I'm not going to go into the details of this, where we basically gave people different levels of autonomy that they could use to be able to feed themselves, where they had control versus it was completely autonomous. And we also told them that autonomous robots can fail. So we artificially introduced failures. They didn't know it was artificial. We just did this in picking up, as well as timing, as well as transferring. And we asked people, what do you prefer? And people, it's very interesting. People said, some people who had very high mobility limitations, they said, even if the robot fails once in every 3 trials, for this task, I'm still going to use this robot because it really makes a huge difference in my life, in the value, the quality of my quality of care. But people who had some arm movements, they only had fatigue when they were like, you would continuously eat. They had said they would only use this robot if it was making errors less than 10% of the time, for example, right? So, again, like technology acceptance is a very contextual question, and it depends on the care recipient and their functional and behavioral traits. Now, recently we have but each of these users, they at least had some neck movement to be able to, eat, except for people with C1 spinal cord injury. Recently we did a study where we did a much wider variety of evaluated this much idea of people who actually could not move their neck. And so the robot had to go inside their mouth to be able to feed them, right? So here is an example of that. You see, like, people with arthropodyasis, C4, C5 spinal cord injury, like people who had quadriplegia, people who had tongue spasticity, masseter spasticity, gag reflex, bite reflex, overbite, all of these actions, right? People had all of these issues, and we are able to successfully feed them different food items that they chose, right? Like here is another example. Here again, tongue spasticity, people who are not able to, people with spasms, limited head, neck range of motion, and things like that, right? A wide range of people. We have also tested this with people in their real homes. Yeah, so but basically the idea was that we also tested this in real home. Like some of these videos were in our collaborators, like medical school, their lab. So, and also we fed people in their homes, right? And in general, people were, like, for example, like comments like this: the technology allows me to do more things on my own, of course, giving me more independence, making me feel more free, and gives me something to look forward to. So it's because of this, again, like, while we are out of the steps that we have taken, there is still a lot of work to be done. And these are the comments that basically, fuel us to keep working with stakeholders to be able to actually one day truly deploy this for long term. Like we have deployed this now for short term, but long-term deployment. Quickly, I want to cover maybe in the next 3, 4, or 5 minutes, I'm going to cover very high level some of the other projects that are going on in my lab. And then I'll conclude and like open it up for questions. So one thing that we realized when we did this feeding study was that this was dyadic, which means one robot feeding one person. But when I went to assisted care facility and I asked people, what is one of the most memorable meal experiences? Almost everybody said eating with friends and family. And so we wanted to see how can we extend beyond dyadic feeding scenarios to social dyadic scenarios. And so there, the challenge of bite acquisition and bite transfer, the same algorithms would work because the food items, picking up food items, whether you do it in a social dining scenario versus this, or putting it inside a person's mouth is the same. What is very interesting is the timing. How do you know when to approach the person to feed? And that is because if you are engaged in social conversations with others, you don't want to interrupt those conversations, right? So here's this project, the Human-Robot Commensality project, where we are looking at bite timing prediction for robot-assisted feeding in groups. So here first, to even start this, we realized there is no data available. So our first step was we actually brought in people and we asked them just eat together, we'll observe. And we collected a human-human commensality data set. All of these data sets are available publicly for you to try out. And then we tried, can we actually predict a user when the user is going to take a bite just by looking at all the co-diners, while first looking at everybody, but then just looking at all the co-diners themselves. So basically, can I predict when you are going to eat just by looking at what the other co-diners are doing on the table, right? And so we are looking at various multimodal features, where they are looking, when did they eat last, what are they talking about, like the gestures and things like that, right? And and obviously this is not like our assumption here is that the people here have already eaten, they always eat together. So there is a social dynamics that is emerging from this. And so idea is that then if there is some kind of social dynamics, then we should be able to pick up items like basically, some kinds of infer the intent of the user who is being fed just by looking at the codiners, because they know when they're talking and when they are looking at something else and when they're eating. So so to finally again to tell you about feeding in general, feeding is a very high impact but at the same time very technically challenging task. And to truly measure the technology progress, again, as I said, like even if you don't remember anything of from my talk, please, it's important that if we are in this field of robotic caregiving or assistive robotics, we need to develop community-centered design processes. We need to involve the community from different levels, from intrapersonal to community level influence. In our lab, we have almost weekly meetings with occupational therapists for this. And it also can benefit from flexibility in the system, because not one thing, just one thing doesn't just work for every user. Every user is different. It brings together various different fields together, whether it's representation, learning, intent inference, shared autonomy, social dining, legible motion planning, deformation, haptics, all of these things. Here are some open data sets and hardware that you can use. All of these are available, or if you have questions, I'm happy to answer after this. Take-home message is robotic caregiving is multifaceted. It is meaningful only with stakeholders in the loop. My lab's goal is to enable robots to assist people with mobility limitations with these activities. And with that, I'll conclude the talk. Thank you.
Thank you so much, Tapo, for the wonderful and thought-provoking talk.
First, let me congratulate you on the amazing work that you've done so far. It's really wonderful to the fact that you've taken what you developed in the lab and actually utilizing it to patients who have found it very useful. So I have a couple of questions in this regard. Like, in your interactions with the patients, how, in your experience, how long did it take for the person to adopt the assistive robot, to incorporate that in their daily lives on a regular basis?
That's a fantastic question. To be very clear, this is still a research phase. They are not using this in their daily life every time yet, right? We have tested this in their real homes, but again, it's for short term. Like, we took the robot to their homes, they tried it out multiple times, and then we brought the robot back, right? So it is still not being used by them for long-term caregiving, as I mentioned, and that is the holy grail, right? Like, that's what we want to go. Having said that, there are lots of things to do to be able to fix it. Like, first, again, while we have taken some promising steps towards generalizability, let's just focus on the feeding task for now, right? Like, every task is different. Even for feeding, to be able to really confidently say that it can generalize to different food items, like, we need to test it out in a long-term setting, right? So for now, what we are doing is we are targeting a care recipient. We are collecting their diet over their month. Generally they have these fixed diet, and then we are trying to see, can it pick up all of these food items that they're eating. And so for technology acceptance, as you've seen, there are, like, we'll have to see how this spans towards some of the subtle preferences that they have during feeding. And so that also is something open-ended. We'll have, like, our system has the flexibility to cater to this, but we haven't tested this in long term yet. So I cannot make any claims about that. But there is some hope, and the goal here is we are basically planning a long-term deployment very soon. So we'll hopefully soon we'll be able to tell you whether they are actually going to use it for long term. Yeah.
Nice, thank you. Just one last question. So what was your rejection rate when you were trying to deploy this?
Fantastic question. Oh, this is a very good question. So I will say this. Whenever we talk about state-of-the-art technology, it's first of all, it's very for people to even try out, forget about technology acceptance for long term. People to even try out these technologies is very challenging because people are very skeptical about these things. Like my students, literally, they one time, we talk with community organizations all the time, even grassroots organizations. Literally, when we were having difficulty recruiting, my students went ahead, we are in New York, right, in Cornell, Ithaca. We went and we heard that there is a disability activism day in front of the Capitol in Albany. My students went there and just started reaching out to everybody there in Albany, in front of the Capitol. Hey, this is what we are doing. Do you want to try it out? Do you want to try it out? And we find that our hit ratio is very low, just for people to even try out. People are skeptical. But what works is, let's say there are some early technology adopters, right? When they try out the technology and then they say, oh, I really liked it, from their word of mouth, from the same community, when it goes to other people, then they start trusting it more and it goes. This is what happened. Getting our first user was difficult. Whenever I moved, I did this in Atlanta, then in basically in UW, in Seattle, and here. When I first moved, getting the first user is always very difficult, or first couple of users. And after that, if you have done a good job of your system, and they start liking it, then with their word of mouth, it was easier to get more and more people there. For long-term thing, of course, there are many things to fix that we are working on now. But yeah, there is a lot of skepticism there. But we need some early technology adopters who are adventurous enough to try this out.
Thank you so much. And I wish you all the best in your future research.
Thank you. Thank you.
Not so much a question, but just I'm a person with a disability myself. I use the Jayco arm. Been using the Jayco arm for over a year now, maybe almost 2. And I can attest to everything that you've said here as being very accurate. And I think your research is invaluable in advancing the goals of assistive robotics. I think you early on in the presentation, you said that a Jayco user said that it would take 45 minutes to eat a meal. I think depending on the meal, that could be very, very accurate. It is a very engaged activity where you are expending a lot of your mental capacity to direct and operate the robot. And that can take away from the social experience if that's what you're doing. And depending on the disability, it can just be very fatiguing or challenging to do. So I think advancing this goal of automated feeding is tremendous, and I look forward to the day when it's generally available to those who need assistive robotics.
Thank you so much, Taylor. Coming from you means a lot, really. Thank you so much. Yeah, I would be very happy to be in touch.
Of course.
Thank you so much, Tapo, for taking the time to come and give us this wonderful talk. I'm sure all of our audience will go back and think a bit about this in the next couple of days and probably reach out to you as well at some point.